Good evening, everyone. Welcome to NPTEL tutorial session for the course Essentials of Oxidation, Reduction, and Carbon-Carbon Bond Formation Application in Organic Synthesis. So far we have been discussing all week's lecture contents, as well as we have also solved several questions as well as assignment questions. So today is our second last tutorial session, and so today I have planned like we will discuss the week 10 and week 11 lecture contents at first, and in the next session, which will be the last session of this tutorial session for this course, in that session we will be having a discussion on the week 10, 11, and 12 assignments, and we will wind up this tutorial session. So we will begin with the discussion of week 10 lecture contents first. Let me take that slide. So in the last tutorial session, or in the last week lecture content, we have seen different applications of this chiral compounds in different reactions like SAMP, RAMP, Diels-Alder reaction, Michael reaction, and we have also seen how aldol reaction and directed aldol reaction takes place under basic as well as acidic condition, and how the syn and anti products will be formed. Like in the case of sin also we can expect two products, and in the case of anti also we can expect two products. So this was the discussion in the last tutorial session, and as well as week 9 lecture content. So today firstly we will see how this aldol products are named. So firstly what we have to do is we have to draw this main carbon chain in like this extended zigzag form. Then isomer with both substituent at C2 and C3 disposed in the same direction, alpha or beta, then the product is called syn, or some people call trio. So if he see here, this alcohol and this methyl group, that is methyl group is in the alpha position, um, no, methyl group and this OH group, that is C2 and C3 functional groups, or C2 and C3 substituents are in same position, means same direction, means we will call it syn, or we can call it erythro. If the C2 and C3 substituents are oppositely placed, when we write in the zigzag form, we can call it anti or thrio. So the diastereoselectivity of this aldol reactions and this aldol products can be improved by using lithium and boron enolates, which are very widely used. Now, stereochemical course of this reaction, which product will be major, the syn or anti, will depend on the thermodynamic or kinetic conditions of the reaction, as well as geometry of the enolate. So, geometry of the enolates means if it is an Z enolate, we will be getting 2,3 syn aldol, and if it is E enolates, we will be getting 2,3 anti aldol. So Z-enolate means if we see this group and this OLI are in same position. E-enolate means this OLI, which is the large group, and this R1 is in the opposite position, opposite direction. So if this OLI is larger than R2, then this is applicable. But if this OLI is smaller than this R2, then this will be opposite. So size of R2 groups also matters. Larger the size of R2, greater the selectivity. Now, if we see this reaction, so here LDA is taking proton from here and this Z-enolate is forming. Then it is attacking over this benzaldehyde to form this one. So since Z-enolate is forming, we are getting 98% of syn. Due to the presence of this bulky R2 group, formation of E-enolate is difficult here. But if we see here it is like a symmetrical compound, so esetinoate is favored, but eenolate is also possible here. So we can observe 70% syn and 30% antiproducts, because it is not that much bulky as compared to tertiary butyl group. So that's why we said if more the bulkier the R2 group, more will be the selectivity. So in general, E-enolate reactions are less stereoselective than with other E-enolates. Or if we use equilibrating conditions, irrespective of the geometry of the enolate, whether it is Z or E enolate, if equilibrating conditions are used, mainly 2,3 anti-aldols are preferred. Now, we know that aldol condensation is easily reversible, and this syn and equilibrium is noticed if the aldol is allowed to stand for a longer time in either solution. So, if we see this to example, so here if it is forming this isodenolate, we can expect either this one 2,3 syn, and maybe this is also possible, that is 2,3 anti, but not so common from isodenolate. But if we take E-enolate, we will be expecting this 2,3 anti product, but there is a chance for the possibility for this 2,3 syn product formation as well. As we can see, the major reason for least likely formation of this 2,3 anti product in the case of isodenolate is the steric repulsion between these two R groups. And here also that is observed in the case of this 2,3 syn product. The steric repulsion between this R and R2 will not favor this, or it will favor this syn product very less. Now, if we consider the carbon-carbon bond formation via boron and silicon enolate, so usually this, if we are using this vinyloxyboranes, in that case, isodenolate gives syn products mainly, and we can observe excellent diastereo selection in such reaction. So, if we see this dibutyl boron triflate and this diisopropyl ethyl nickel complex is used. So if in that case this boron enolate is forming, that is attacking over this benzaldehyde, and here we are getting 97% of syn product. So why the cis enolates are formed in most cases with vinyloxyborane? Because if we see this transition state where this, yeah, this is represented like this. So this boron will coordinate with this oxygen, and This B isodenol, this is the formation of isodenolate, but for the formation of this E-enolate, it requires a transition state like this, where this methyl group and this ethyl group on the starting material will come in the same, or it will come nearby. So that is not favored because of steric hindrance. So that's why this E-enolate is generally not favored and isodenolate is favored in such cases. So here, as we can see, this methyl and this ethyl are in same phase, but here it is in the opposite direction in the case of isodenolate. And if we use this DIPEA, which is a more bulkier base, it permits anti-deprotonation. That is, deprotonation takes place opposite to that of the takes place from this anti-complex. So it will favor this isodenolate. But if in the case of we are using lesser bulkier base like triethylamine, it will permit syn deprotonation. So in that case, this E-enolate will be more favored than isodenolate. So this is the syn complex. So this, there will be sterically bulky steric substituent. So with sterically bulky cy substituent on B, transition state 1 is less favored. So here in this case E is more favored because this substituent on this boron is also sterically hindered. So that's why it is favoring E enolate. So as we can see here, if we use this boron complex substituted with this butyl group, we are getting isodenolate. But if it is more sterically hindered cyclohexyl group on the boron, we are getting E-enolate. Now, if we see the use of this oxazolidinones for the controlling the selectivity of this aldol reaction, so here we can see this is the oxazolidinone attached ketone. So here, as we see, when this metal we use, it will coordinate with this both this ketone as well as this oxygen. So it will give rise to this transition state. So where this R group and this group is trans, and as we can see, the preferred phase of attack will be this bottom phase is blocked, so this phase will be more preferred for the attack. So we will be getting one product only. So if we see here, this this phase is blocked, so we will be getting the above allylated product, and then hydrolysis of this auxiliary will remove that, and we will be getting this one. So these are different compounds which we can use for providing the selectivity, or from which we can prepare this oxazolidinones, that is S-valinol, R-valinol, S-phenylalanine, 1s2r norepinephrine. Now if we see this one, if we are treating this with base, so it will abstract proton from here. But here, as we know, when we quench with an electrophile, which phase it will come? So here both phenyl and this methyl group are below, so the electrophile will be coming from the above phase. So this will be the major product. And when we are using this methylide and NHMDS, we are getting 93 is to 7 diastero selectivity, and with this um, benzyl bromide and LDA, we are getting 98 is to 2 diastereoselectivity selectivity. Now if we see chiral aldol reaction, so that is what we said about using this oxazolidinone. So same thing, using this Unix base, we are abstracting proton and forming this enolate. So this is Z boron enolate, where this bulky groups are trans to each other, then quenching with aldehyde gives this product. Because this is below, so the incoming electrophile will be coming opposite phase, and we will be getting this product, and then LiOH will remove this and give this carboxylic acid. So the geometry of the enolate will determine whether the product will be synaldol or anti-aldol, and the stereochemistry of this auxiliary will determine whether this absolute configuration. So two things we have to consider, whether it will be, so in the case, so in this itself we have other possibilities, because we said that this is below, so anyway methyl or the SAR group will be coming from above phase. But if it is coming from above phase also, this OH can be below. Or in the other hand, if we consider, if this is Z boron enolate, it will give synaldol. So synaldol means OH and methyl can be same side, or that like OH and methyl can be either above, or OH and methyl can be below. So that's what it is given here. So this syn or anti-aldol, that will be controlled by the enolate stereochemistry geometry, that is whether this uh, enolate is Z or E. So Z enolate will give synaldol, E enolate will be giving anti-aldol. And the absolute configuration, whether the incoming electrophile will be above or below, that will be controlled by the chiral auxiliary. So the stereochemistry of the auxiliary determines the absolute configuration. So that is the 2 points which we have to consider while doing chiral aldol reaction. Now, another other some factors which will control this reaction is that the oxazolidone is essentially an amide and of significant size. So, mostly which will be favored is adenolate will be formed, because this two groups will be trans, that will be more preferred. So, we will be getting isodenolate and synaldol in most of the cases. Now, even though there is a chelate in the boron enolate, when the aldol reaction occurs, chelate must fall apart, or else there is no Zimmermann Trassler transition state. And when the chelate is gone, there is repulsive dipole-dipole interaction between the oxygen atom. So the dominant conformation flips 180-degree. So the result is what will be the product, aldol product, but relative to the oxazolidine, the phase of attack is opposite from alkylation. So this is what I just explained now. That is what is given here, so we can write this is like this. So here we can see there is a dipole repulsion, so this is more favor transition state. And as we can see, this is controlling, so the attack will be from the opposite phase of this, so this will be the major product and sin will be the major product. And one more thing is that using this boron enolate, we can have more selectivity compared to the alkylation using Evans auxiliary. Now, reversal of diastereoselectivity. So, how we can reverse the diastereoselectivity? If we use this Lewis acid like diethyl aluminum chloride, it will coordinate with this aldehyde. Therefore, the boron enolate will not be affected. So, boron enolate will not have to coordinate with the aldehyde. This aldehyde will be coordinating with this diethyl aluminum chloride, which is also a Lewis acid. So, boron enolate will not have much influence on whether anti or syn diol is formed, but the dipole dipole interaction will be still a deciding factor in that case. So you may just quickly go through the aldol reaction, then we will go to the next topic, that is Claisen rearrangement, which is another example for application of using this enolates. So there are several classification for this Claisen rearrangement, including Ireland Claisen rearrangement, so that we will see maybe in few minutes. So if you have any doubt with this aldol reaction, chiral aldol reaction, and this use of this oxazolidinones in controlling the stereochemistry, and how enolates determines the diastereoselectivity of the reaction, then we will go to the next topic. So now if we move to the next part, that is Ireland clays and rearrangement, where we can see the importance of the geometry of phenolates. So So if we see this particular compound and we use LDA, it will abstract proton from this center and then attacking over this dimethyl tertiary butyl silide chloride, we will be getting this particular enolate. So if we use this THF as the solvent, this trans enolate we will be getting, where we can see this R and this R1 group is in cis format. And if we use HMP and THF as the solvent, we will be getting this R and this R1 in trans form, and this OX and this R in cis form. So this will be giving this cis product and this will be giving this trans product. So if we see this particular compound in THF, as I said, this is giving cis product. This also in THF it is giving this cis is giving this trans product. If we use this THF HMP on this trans product, we are getting trans compound, and if we use it in cis product, we are using this we are getting this cis compound. So this E double bond that is present over here will be leading to this E transition state in THF solvent, which will be giving this cis product. And in the case of this one, yeah, this E double bond in THF HMPA will be giving this trans product. So this is just to show that the solvent also plays role in controlling the diastereo selectivity of the reaction. And why this is happening, and why THF is giving one product, and why the mixture of THF and HMPA is giving another product. So as we said, in THF specifically E-enolate will be favored, and in mixture of THF and HMPA isodenolate is favored. Why that is given here. So in THF, where intramolecular chelation is possible, then interaction of C double bond O versus methyl and C double bond O versus H are important, keeping the steric offered by the R2 group. So this determines the fate of E and Z with respect to methyl and O, this lithium in the final enolate. So here, as we can see, so this type of a chelation is possible in the case in between this C double bond O as well as this methyl group and the C double bond O as well as this hydrogen when we are using THF. So in the case of THF, mostly this E enolate will be favored, that will be having this kind of geometry. Now, in the case of this THF HMPA mixture, there is no such chelation observed. So, this type of enolate is not favored in that case, but rather than that, normally whatever is happening, that is Z-enolate is favored. That is usually favored in that case because this HMPA is preventing that chelation. So, in HMPA, the cyclic transition state is not possible since HMPA coordinates with lithium plus. The methyl group prefers to be away from the OR1 group. So as we can see here, yeah, so methyl group coming at this position will not be favorable, and therefore this enolate will not be favored in the case of THF HMPA mixture. So the factor is that cyclic transition state formation will not be favored due to the absence of chelation in the case of THF HMPA mixture. Now the next reaction is Claisen rearrangement. So Claisen rearrangement is allyl or aryl or vinyl ethers upon heating. Vinyl ethers upon heating undergo rearrangement. So it is basically a 3,3 sigmatropic rearrangement, and it is a highly stereoselective reaction, and it proceed via a chair-like transition state. So if we see this compound, and we will number it like starting from this oxygen, we will number this like 1, 2 prime and 3 prime, and this will be 1, 2, 3. So basically what is happening, this 1 prime bond will be getting cleaved. 1 prime bond will be getting cleaved, and there will be a new carbon carbon bond formation between this 3 prime position and 3 position. So mechanistically what is happening, this is this oxygen lone pair will fall over this here, and this will come over here, and this will come over here, and this is breaking. So that is happening here. So if we see the product, it will be like this one, which again will aromatize to give this compound. So this is basically what is Claisen rearrangement. It is a kind of 3,3 sigmatropic rearrangement, and it proceeds via a chair-like transition state like this. So if we see this two possibilities, that is, this is also favored, this is also possible, and this is also possible. So what is the difference between these two is the position of this substituents R2 and H. So here this R2 is equatorial and here R2 is axial. We know that bulkier groups will be preferring equatorial position rather than axial position. So this will be the favored transition state, and it will give rise to this E product, and this Z product from this transition state will be less favored. So same thing is happening here also. So if we number it, it will be like 1, 1 prime, this will be 2 prime, and this will be 3 prime, and then this will be 1, 2, 3. Then this will interact and this will be breaking, so we will get this transition state which will give this particular compound. And if we see this example, so what is happening here, this, what is the major difference is this one. So here this both the protons are in cis fashion, and here it is trans, so it will be giving this particular product. So if we change the configuration at this allylic double bond, we can get different configuration in the product. Since the reaction is concerted, the chirality is transferred into the product. Whatever chirality is already in the starting material, that will be directly transferred into the product as well. So the geometry of the initial molecule is important. So if we are, what to say, if we are starting with this EE, it will be going through this particular transition state, that will be, so as in the starting materials, this methyl and this methyl will be in trans position, and we will be getting this product, and here also this will be in trans configuration, so we will be getting this product. So if we see this also, here ZE and this EZ, this is going through different transition state, the geometry of the transition state, but the product we will be getting will be the same. So this Claisen rearrangement usually requires very high temperature, and usually it is exothermic reaction, and energy is about 84 kilojoule per mole. So as we said, it is a concerted pericyclic reaction following superficial reaction pathway. Now, this solvent effects can also be observed in this Claisen rearrangement. So, if we use polar solvents, it will accelerate the rate of the reaction, and if we use hydrogen bonding solvent, it will also increase the rate of the reaction. For example, if we use the mixture of water and ethanol, it will give tenfold higher rate constant than in sulfonyl, where there is no such hydrogen bonding factor. And usually, Lewis acids are also used in some cases to accelerate the reaction. This Ireland Claisen rearrangement, this we have already seen, so I'm not going into that again. Now, if we see this aromatic Claisen rearrangement where we use this allyl phenyl ether, so we can see here, so this we can number like we said, we just saw this example 1, 2, 3, and this will be other 1 prime, 2 prime, or 3 prime. Then we will be getting this product when we heat it at higher temperature, and once it re-aromatize, we will be getting this particular product. Now, as we know, as we saw here, so just what is happening, this whole allyl group is just shifting or migrating into the ortho position. But if ortho position of this aromatic ring is blocked, then para position can also, substitution at this para position can also occur with the retention of configuration. So as we see here, both this ortho position are blocked, so this group, firstly it will go through this transition, then it will again come here and give this particular compound, and then rearomatization will give this product. And another example is Johnson Clayton rearrangement. So it is not with aromatic compound. There we are taking this type of compound and we are using this triethyl formate type of compounds, and that will first give this particular intermediate. So what is happening? This oxygen lone pair will attack over this carbon, and one of the OET group will eliminate to give this transition state, and another OET get protonated with the help of this acid catalyst which we are using. It will give this compound. Then if one ethanol get eliminated, we will be getting this type of compound. Then it can undergo this 3,3 sigma tropic rearrangement, and it will give this particular product. So that is known as Johnson Clayton rearrangement. So how we can prepare this kind of allyl vinyl ether for using in this Johnson Clayton rearrangement? So if we start with this alkyl vinyl ether and use this kind of compound in presence of acid catalyst, we will be getting this type of product. And another possibility is by using this selenoxide type of compound and we heat it, it will be giving this particular intermediate by, yeah, elimination of this group, and we can, from this we can get this by 3 sigma tropic rearrangement. And again, if we use this type of alcohol and this vinyl iodide compound in presence of copper catalyst and cesium carbonate, we can expect this type of Ullmann coupling type of reaction in the presence of this tetramethyl phenanthroline ligand, and we can get this compound, and this is also another substrate for this Claisen rearrangement. So far we have discussed this Claisen rearrangement, aromatic Claisen rearrangement using this allyl phenyl ether, and how this para products can also be formed from aromatic Claisen rearrangement. And now we have also seen this Johnson Claisen rearrangement. Now another reaction is Eschen-Moser Claisen rearrangement. So there, what is happening? If we are treating this type of alcohol with this Eschen-Moser salt kind of reagent, no, this type of amine complex in toluene and reflex, we will be getting this type of compound. So here what is happening, this oxygen lone pair is attacking over this carbon, one of this OMe will be leaving, and then again elimination of this methanol will give this type of compound. And then again same 3 sigma tropic rearrangement is possible on this Eschen-Moser salt kind of compound, and we will be getting this product. So that is known as Eschen-Moser Claisen rearrangement. So detailed mechanism is given here. So firstly, this nitrogen lone pair falls over here. OMe will eliminate to form this compound. Then this oxygen lone pair will attack over this carbon, stabilizing this positive charge on nitrogen to form this intermediate with positive charge on oxygen. Then what is happening, this OMe minus will take this proton and this bond will shift over here. It will stabilize this positive charge on this OMe, and then this 3 sigma tropic rearrangement can happen and give this particular product. Now same similar example we can see here also. Firstly, the formation of this amine complex, and then this elimination will give this type of intermediate. Then this Claisen rearrangement will take place to form this compound. Again, it is going through this type of reaction first. Now, another modification of the Claisen rearrangement is Bell's-Claisen rearrangement. So, there what is happening? Allyl ethers, amines, and thioethers with ketene leading to gamma delta unsaturated esters, amides, and thioesters. So, if we see this particular example, so this substrate we are taking, so that can be either allyl ether, amine, or thioether. That is, the substituent X can be oxygen, sulfur, or nitrogen. And then if it is attacking over, if it is reacting with this gamma delta unsaturated ester, amide, or thioesters, it will give this particular rearrangement. And here, then this Claisen rearrangement is taking place to form this type of compound, that is known as Bell's-Claisen rearrangement. Now, another classification is this heteroclaisen rearrangement. So, one among that is Asa-Claisen rearrangement. So, as the name suggests, we know that Asa-Claisen rearrangement means it will be moving through nitrogen atom. So here what is happening, an iminium ion can serve as pi bonded moiety. So in all the previous cases what we saw was alkene was acting as a pi bonded moiety where only carbon was present, but here iminium ion can serve as the pi bonded moiety. Since another, so it will be giving this type of intermediate first in the presence of n-butyl lithium. Proton abstraction will take place and this positive charge will be stabilized. Then same like 3 sigma tropic rearrangement. So it will be like 1, 2, 3, and here 1 prime, 2 prime, and 3 prime. So this bond will be formed and this bond will be cleaved. So we will be getting this particular product. So that is an example for Asa-Claisen rearrangement. Now, another example for heteroclason rearrangement is thiaclason rearrangement. So, thia means it will be involved with sulfur. So, again, secondary butyl lithium and R bromide can give this product. Then, upon heating, this 3,3 sigma tropic rearrangement will take place, which will give this product. And then, this particular functional group can be converted into ketone to get this compound. This all what we see was 3,3 sigma tropic rearrangement, that is Claisen rearrangement. Now related to this is another reaction, that is 2,3 sigma tropic rearrangement. So there what will be happening? This is attacking over here. This is coming over here and this is breaking. Hmm. Yeah, so this will be 1, this will be 2, this will be 1, 2 and 3. So bond will be forming between this second carbon and this third carbon, and this 1 prime bond will be breaking, so we will be getting this particular in compound. So this is the another example for that, where we can synthesize this gamma cyclocitral, and 6 electrons should be available for this kind of electrocyclization to take place. That is one requirement. So now the next topic is this hydrolysis of this thioketal. So this is an example for thioketal, and if we use this mercury chloride and acidic condition, firstly this sulfur will coordinate with this mercury, so it will give this particular intermediate. Then this bond is breaking, so this will be shifted over here, and we will be getting this particular intermediate. Uh, and if we are using this HCl here, what is happening, this will be protonated and we will get this particular compound. So this, I think, yeah, so here we saw this type of compounds can be converted into this ketones or aldehydes. So basically we are using it for the protection of this ketones or aldehydes. So this thiophenol or this dithiene compound can be used for the protection of aldehydes or ketones. So this is just to show how we can recover our ketone or aldehyde from that protected compound. We can use this acidic condition for that hydrolysis of thioketals. Now, next reaction is this Chenma rearrangement. So, what that is 3,3 phosphorimidate rearrangement, or we call it as Staudinger rearrangement. So, this firstly, this alcohol forms phosphide, and then Staudinger reaction convert that into amine. So, as we know, this phosphorus oxygen, this P phosphine oxide is more stable than this P double bond and compound, and this is the driving force for this reaction. So, what's happening here is, firstly this base will abstract this proton, and that will attack over this phosphorus, and this chloride will leave to give this compound. Then this Rn3, this Schrodinger reaction will take place with where this p double bond and bond is formed. Then, as we saw earlier, Claisen rearrangement will be taking place. So this is the Schrodinger reaction. So from this acid compound we are getting this type of compound. So then if we do the workup, we can get this amine. So what is happening? Firstly, this ppH3 will attack over this nitrogen, and we will be getting this particular intermediate, and then it will form this type of, it is like a modified kind of Wittig reaction, we can say, where this four member transition state will be formed, and then this N2 will be released and give this compound. Then aqueous workup will give rise to this particular amine, and this ppH3 oxide will be eliminated. So that is why it is said here that p double bond, or this will be more stable than this one, that is the driving force for this reaction. So far we have seen different type of Claisen rearrangement: Eschen-Moser Claisen rearrangement, Bellis Claisen rearrangement, heteroclaisen rearrangement, then Chenmap reagent, and in between we have also seen the 2,3 sigma tropic rearrangement also. Now, another example for this Claisen rearrangement is switcher ionic Claisen rearrangement. So, we have said earlier that usually this Claisen rearrangement requires higher temperature, or it is usually an exothermic reaction. But if we are doing it in the presence of some Lewis acid, or this particular classification, that is switcher ionic Claisen rearrangement, we can carry out this reactions at room temperature or below. So here, as we can see, what is happening, this nitrogen lone pair is attacking over this carbonyl carbon, and the Cl minus is eliminating. So this will go first, and then it will come back, and Cl minus will eliminate to form this particular intermediate. So this can be written in this particular form also. Then 3,3 sigma tropic rearrangement will take place to give this particular compound. So this type of reaction, so why it is called Switter ionic Claisen rearrangement? On here positive charge and here negative charge is present in the same compound, that's why it is classified as Switter ionic Claisen rearrangement. So this type of reaction, so here as we can see, it is taking place at 0 degrees Celsius. Usually this Claisen rearrangement will need more than 200 degrees Celsius at least, for the reaction to complete, and here this type of reaction will occur in 0 degrees Celsius or below that also. Now, if we see this, already we have discussed in the previous lectures, that is chromium type of oxidation. Basically, this oxidative transposition using PCC, PDC, and IBX. So that is also type of Claisen rearrangement. So what is happening here? This Yeah, from this particular compound, we can get this one. So if we see the position of this double bond, it is here, and here it is here. So it is a type of Claisen rearrangement. So firstly, PCC will form this particular intermediate. So PCC is pyridinium chlorochromate. So that will form this one. Then a Claisen rearrangement is taking place to form this particular compound, which upon removal of this particular chromium, we will be getting this. So it will take this proton, and this bond will shift over here, and we will be getting this ketone. So if we compare the starting material and the product, we know that it is like a 1,3 enon transposition. So here also same thing is happening with this PCC. This type of reactions are possible. Next reaction is this Overman rearrangement. So Overman rearrangement is using this allyl trichloroacetimidates. So allyl trichloroacetimidates means we are using this one, and that will form this with this alcohol. It will form this intermediate, and then we when we heat it, this type of this nitrogen lone pair will attack over here. This bond will shift over here, and this is breaking and coming over here to form this one. Then NaOH will be removing this whole group, and we will get this allylic amine. So allyl trichloroacetimidates to allylic amines. That reaction is known as Overman rearrangement. So same thing is happening here also from this one. So basically, if we see the reaction, what is happening, this double bond shifted here. So this whole functionality come at this position. So instead of OH, we will be having NH2. So same thing, both this OH is converted into NH2, and the position of double bond also shifted, and we got this product here. So that is Overman rearrangement, allyl trichloroacetimidates to allylic amines. Now the next reaction is Bamford-Stevens and Shapiro reaction. So here what is happening? This type of hydrazone is getting converted into this type of compounds, uh, which can be either E or Z. So what will be happening? The basic mechanism is that firstly, when we use this NaOMe heating and protect solvent condition, this nitrogen lone pair will shift over here. Deprotonation takes place first, and then tosyl group will get removed to form this compound. Then again, this nitrogen negative charge will come over this position, and this will be taking this proton to form this one. Then N2 group will be eliminated to form this compound. Then this from here, this proton abstraction will take place and stabilize this positive charge to form this alkene. This is the case when we are using protic solvent. Now if we use this aprotic solvent, what difference it will make us? It will be already this negative charge over here, and once N2 will leave, instead of this carbocation, it will be this particular intermediate, so that we can write like this. Then again this R2 is migrating over here, and this will be taking this proton to form this kind of alkene. So the reaction can take place in protic solvent or a protic solvent, but the product will be depending on which solvent we are using. Now the next one is Shapiro reaction. So in the case of Shapiro reaction, this lithium will be coordinating with this hydrazone, so it will give this particular intermediate, and then again the same reaction will be happening in Shapiro reaction also. So far we have seen this Witter ionic Claisen rearrangement, chromium oxidation, Overman rearrangement, Bamford Stevens, and Shapiro reaction. Okay, we have half an hour more, so we will cover some more topics in today's session. This is another example where if we are treating this allyl silane type of complex with this MCPBA, so as we know MCPBA will carry out the epoxidation of this alkene, to give this epoxide, then LAH will open this epoxide and give this alcohol. Then if we use PCC, it will oxidize this alcohol into this ketone to give this product. So this nucleophilic attack on the carbon alpha to silicon, that is considered to be favored by simultaneous interaction of the approaching electron pair with antibonding. So it is shown here. Yeah, so there is a stabilizing interaction here between the electron pair of the antibonding orbital of the epoxide carbon and the vacant 3D orbitals of the silicon. So that is favoring the nucleophilic attack on the carbon alpha to silicon. Now some reactions which is similar to this aldol reactions involve reacting this. So if we use this, So firstly, this aldol reaction will be, or this negative charge will form here, and it will attack over this one and give this homoallylic alcohol. Then we can use this homoallylic alcohol for different reaction like epoxidation, ozonlysis, hydroboration, dihydroxylation, olefin metathesis, cycloaddition, and hydroformylation. So if we see here, this crotyl based reagents if we are using, so what is happening, firstly this product is formed, and uh, like why this kind of products are not favored, that is the question here. So this, maybe we will have this discussion later. So now if we see this allyl silanes, if we are taking this type of compounds and we are treating with this trialkyl silyl halides, we will be getting this allyl silane. Correspondingly we can prepare this allyl boranes, allyl stannanes, and allyl boronates. So this compounds, this allyl silanes, allyl borane, allyl stannine, allyl boronate, this can be used for different types of reaction in organic synthesis. So different reagents of this allyl silanes and all will require different uh, different reaction medium or different reaction conditions to react and to form. So if we consider this allyl silane, it will need strong Lewis acid condition, and allyl stannane require moderate Lewis acid activation or heating condition. Now allyl borane can react with aldehyde in the absence of activators even at minus 100 degrees Celsius, and allyl boronates can react with aldehydes at room temperature in the absence of any activators, although it will be slow reaction. So if we see this particular example, so this can exist in this both forms, where this metal can be magnesium lithium or it can be potassium. If it is magnesium and lithium, the equilibration will be quite fast, and if it is potassium, it will be quite slow. So what will happen, firstly this tertiary butoxide, potassium tertiary butoxide and n-butyl lithium will form this compound, and then treating it with this trimethoxyborane will replace this potassium with boron, and we will get this compound. Say again, if we are treating this one, we will be getting this compound, then boron, treatment with boron will give this one. So if we treat that with aldehyde, what will happen, so here we can see this both are having trans stereochemistry. So it will react with this aldehyde to form this particular intermediate, and this will not be favored. So what is the difference, this Y and this group is having trans stereochemistry, in this is having cis. So that is not possible because in starting material both are having trans stereochemistry. So it will give this particular product. Mm, no. So it, this will also give, if we are taking this cis one with this aldehyde, it will not give this particular intermediate, it will be going through this one where these two groups are in the same side. So that is the difference when we use a different starting material. Trans will give this one and cis will be giving this one. So these are some more examples for that. I'm not going into detail. Now the next topic is allyl indium chemistry. So indium chemistry is useful as it is comparable to other transition metal based chemistry. So indium, we know it is used in semiconductors also. So and it is also useful like samarium and all, it is also useful in single electron transfer reactions. Now indium exhibit low heterophilicity in organic reaction generally. So with this indium reaction, this oxygen and nitrogen functional groups are usually tolerated, whereas zinc and tin readily generate the corresponding organometallics or enolate. So indium, we know the configuration is 4D10, 5S2 and 5P1, and using this many chemoselective transformations can be observed. Then novel carbointations can be performed by direct reaction of this indium metal or indium salt with this organic substrate. So it will give this type of compound through a one step procedure. Also, that is this allylic halides can also react with indium to form species in THF or DMF as a solvent. And usually these two solvents are preferred, THF or DMF. In other solvents the reaction is somewhat sluggish. So here if we see what is happening, this is attacking over this aldehyde and we are getting this particular compound. So indium reagents react at the gamma position and alpha beta unsaturated carbonyl compound lead to 1,2 addition product exclusively. So if we consider this aldehyde, only 1,2 addition is happening. So allyl attack is happening at the 1,2 position using indium to give this type of compounds. So if other groups like hydroxy group, ester group or cyano group, that is usually unaffected when we are using indium reaction. So usually if we see this barbier allylation type of reaction, we use their zinc generally. So this is a type of barbier allylation where alkylation of carbonyls with alkyl halide and metal take place, which is usually done with zinc. So it can be done with indium also. Um, and the reaction can be done in water as well. So this barbier allylation is the name comes after this Philip Barbier, who was a teacher of the Victor Grignard. Now exception where reaction occurs at alpha position. So if we consider this particular example, firstly this is formed. So here instead of mm, yeah, if we use this tributyl tin chloride, this is getting replaced with this tributyl tin where we can observe both E and Z mixture with E is getting predominant here. So here the attack is taking place at the alpha position to give this particular product. Again, these are the similar reaction where we can see how this stereochemistry can be controlled and how this alpha pinene can be converted into this beta pinene using this indium. So this addition of this kind of allyl indium reagent to aldehydes which have substituent at this alpha or beta carbon are very diastereoselective in the aqueous system. So if we consider this alpha oxyaldehyde, here the major product is syn product, which is chelation control, and this anti is minor product and no chelation is observed. So it will go through this type of chelation with this indium which will give this type of intermediate, and only this is observed where this OH and OH are having same stereochemistry when we write in the zigzag form. So as we said earlier, this like zinc and this tin also, indium can also be used in aqueous medium, and there is no formation of any coupling product observed. So this is another example where firstly this is forming, then the silver oxide is carrying out this transposition, that is sigmatropic rearrangement to get this particular compound. Now, if we see this alpha haloesters and allyl chlorides, they are also commonly used. So, this aldehyde firstly react with this one to form this compound, then NaH can undergo carry out epoxidation. So, proton abstraction will take place from this center. It will attack over here. Cl minus will leave to form this particular compound. Same with this also. This is attacking, one to attack will take place first to give this compound, then base will abstract proton, again epoxidation will take place, Cl minus will leave to give this compound. Same like similar also here also what is happening firstly, okay, so here this is attacking over this center. Mm, so here indium will be coming. Yeah, then this is coming over here, and this position it is attacking over this center to form this intermediate, and then this lactonization will take place between this ester and alcohol. This hydroxyl group will attack over this carbonyl carbon, and it will give rise to this product. So these are some more examples for this indium mediated reaction. So similarly, as we said, allyl tin compounds also add to carbonyls, with which will undergo through this uh, chair-like transition state, which can give either syn product or anti-product, and this usually takes place under heating condition. Yeah, so this is about week 9 and week 10 lecture contents. So with this we will conclude today's session. So in the next session we will be having only question discussion. Today we have not discussed any questions, we have been covering up the portions. So in the next session we will try to solve week 10, 11 and 12 assignment questions, and if time is there we will discuss some more questions, and next session will be the last tutorial session. So thank you for joining. See you in the next tutorial session.